I'm Amanda Randles. I'm the Alfred Winborn Mordecai and Victoria Stover Mordecai Associate Professor of Biomedical Engineering at Duke University. The crux of all the research in my lab is one software code called Harvey, and it allows us to take in data that you're deriving from CT images, from MRI images. So you get patient-specific geometries from their medical images, and we're running large-scale blood flow simulation on massively parallel supercomputers to get patient-specific personalized flow models down to the cellular resolution. Harvey itself is based on a regular Cartesian grid. It's essentially a stencil application, and it is very, very bandwidth limited. There's a lot of point-to-point communication, nearest neighbor communication between each of the nodes, and the high bandwidth memory that's provided is essential for really getting high performance. So we've been working with Sunspot at Argonne to try to get ready for Aurora, and that's been a very useful process to really see getting the bugs out of the code early and trying to identify, as we're moving to a sickle representation of the code. We're trying to build patient-specific models to essentially create a digital twin of the human that physicians can use to find disease and diagnose disease better, track the patient over time when they're not in the physician's office. One of our big grand challenges that we're focused on now is trying to move from modeling single heartbeats to how do you actually model someone and track them over a week or a month or the best case scenario, a year. We're trying to use AI in our research to really advance our cancer models and allow us to understand, the trajectory of cancer cells, the effect of different properties of the cancer cell, like its size, its deformability. Using Aurora, one of the big focuses of our project is trying to bring in situ visualization, in situ machine learning training. And what we mean by that is really addressing this big data problem of, in these large simulations, we are generating petabytes of data every single time step. And it's really not possible at that stage to output all of the data and do, post hoc analysis on many petabytes. But if we want to use it for machine learning training, or we want to be able to visualize hundreds and hundreds of millions of cells as they're moving over a long period of time, we're working with the Argonne teams to figure out ways to actually visualize the data while it's still in memory on Aurora. It's allowing us to interact with this data in a way we never could have before. I'm very excited about this idea of the digital twins and how do we actually create a digital twin of a patient and build that going forward. And just in general, it's a lot of fun to play with the world's biggest supercomputer.